Okay. So, hello everyone. Welcome to the Temporal Graph Reading Group today. We are very happy to have Sahil today, who will be presenting his paper Graphene, Learning on Graphs with Heterogeneous and Dynamic Feature Sets at ICML 2023. And just a quick introduction about Sahil. Sahil is at the Department of Computer Science at the Indian Institute of Technology, Delhi. He is a PhD scholar at the IIT Delhi, working under the supervision of Prof. Sayan Ranu. And Sahil works in the area of learning to solve graph optimization problems with focus on combinatorial optimization, graph neural networks, lifelong learning, and generative modeling. He is also interested in applications of computer science concepts in other fields such as VLSI chip design and material science to discover new materials. He has interned at prestigious institutions such as the University of Tokyo, Never Labs France, and Qualcomm AI Research Amsterdam. His research works have been published in conferences such as NeurIPS, AAAI, ICML, and ECML PKDD. Additionally, he has one US patent granted to his name. Sahil has been the recipient of the Qualcomm Innovation Fellowship of the year 2022. And let's welcome Sahil for his talk today, and we'll let people joining from the waiting room. Yeah.
Thank you very much for the introduction. Thank you very much. And thank you very much for inviting me. Let me try to share my screen. Yeah.
And do you prefer to answer questions during the talk or like after the talk at the end?
During is fine, I think. I mean, because otherwise at the end something comes up, then we have to go in the start. I mean, you can ask questions as interrupt me, no problem. I mean, interrupt me whenever you want.
Okay, sounds good. Thanks.
Thank you. Give me a second. Okay. Are you guys able to see the screen?
Yes.
Okay, excellent. Yeah, so whenever there is, I'm not sure if I can see the chat section. So if there is anything, just interrupt via audio. Okay. Any doubt? Okay.
Okay, sounds good.
Let me just minimize it a bit more. Great. Yeah. So I'm Sahil. Thank you for the introduction and for the invitation. So I'll be presenting my work, Graphene, Learning on Graphs with Heterogeneous and Dynamic Feature Sets. It's a joint work with my another PhD student in my department, Shubham Gupta, and my advisor, Professor Sayan Ranu, and a collaborator, Professor Shrikanta, and we are all from IIT Delhi. This work was published in ICML 2023 in Hawaii. Yeah, so you all guys, I guess you all know about graphs. They are widely used to model complex systems which may or may not be dynamic, such as social networks, for instance, Facebook, Instagram, where the nodes can be users and an edge between them could represent some interaction or friendship relationship between the users in the social network. Graphs are also widely used to model components like, things like molecules, where a node could be an atom, and edges between two nodes could represent bond between the atoms. And these graphs can also be attributed. For instance, in the case of molecules, node could have types such as it could be carbon, hydrogen, oxygen, and edges could also have types such as a single bond, double bond, triple bond, etc. And you'll also see graphs in networks, the interaction networks or shopping networks, etc., where nodes could be items or users, etc., etc. So recently, I mean, I won't say recently, but like last 6-7 years, there has been a wide interest in using machine learning for graphs. And you might have heard all these kind of tasks such as node classification, link prediction, graph classification, etc. Let's take an example of like one of the tasks that is popularly known as node classification, where you have a graph and each node has certain types. I mean, a node could belong to a certain class, such as, I mean, think of like a citation network where a paper cites another paper, and the goal is that you want to tell, okay, what kind of, you want to classify the paper into a particular category. For instance, you want to classify, okay, paper A will belong to computer science category, or physics category, or biology category. This kind of task is popularly known as node classification task. And there are tasks like graph classification, where you have like a molecule, where molecule essentially like a set of atoms and a set of edges between them, and the goal is you want to classify, is the molecule active against a certain cancer line, etc. Or you want to do a regression task, where you want to predict the solubility of a particular molecule, essentially a graph structure. And recently, graph neural networks, graph transformer, etc., have shown like really good performances on these type of tasks. And yeah, as I mentioned, GNNs are doing a pretty good job on these kind of data sets. Essentially, they capture the topology of, I mean, a node captures the topology of the neighboring nodes, etc. In the case of an MPNN, I'll take it, I mean, just for the sake of completeness, let's see how a GNN works. Essentially, you have, let's say, a target node, let's say the node number 5, and a GNN generally constructs a computational graph based upon its neighborhood. So for instance, if you want to construct the embedding of node number 5 for layer 2, it requires the embedding of its neighborhood at layer 1. So node 5 would require the embedding of node 1 and 4 at the layer 1. And to construct the embedding of node 1 at layer 1, you need the representation of node 1's neighbor, essentially 2 and 5. And for this, you need the, for example, you can see the input node features of the node 2 and 5, right? And the input node features in case of a citation graph could be the represent some word embedding representation of the abstract. It can be bag of word representation also. In a co-shopping graph, it could be like some item properties, like if let's say it's a beverage company, then it might have, okay, calorific content, etc., etc. So although GNNs are doing a very good job, one thing has been seen in a lot of data sets that people have applied GNNs on, that you need very good features as input. And a lot of GNNs assume that you have access to all the features of a particular node. So let's take an example. You might have like a dating company, where you have a, let's say, user 1 and a user 2, and the company is maintaining features for each user, such as the age and the gender of the person. For example, user 1 has age 22 and the gender is female. But sometime what could happen, and GNN could work very good on it, but sometime what could happen is user 2 decides to hide his or her age. Actually, he or she is not willing to show his age, or maybe he or she has not entered the age, forgotten to add it. Then in that case, your input node features might not have the information of that particular nodes attributes. I mean, some attributes might not be available actually. And generally, it has been seen that GNNs work very good when you have the attribute information of all the nodes in the graph, right? Sometimes GNN cannot be even executed if you don't have that information, right? So that's one scenario. And another scenario is, let me just 1 minute. Another scenario that we come across is that, okay, first case was all features are not available. Sometimes what could happen is features at different nodes might not be actually applicable to other nodes. So let's take an example of a shopping kind of a network, where you have products like CPUs or like computers or beverages. So if you want to have like homogeneity, right? So for example, soft drink could have features like how many calories, what's the capacity of the bottle, like in milliliters. But if you have a shopping network, then in the network, it might be relevant for a computer to have feature like CPU cycle, right? But it might not be relevant for a soft drink to have a feature like CPU cycle. Like, it's like different nodes could have different features where heterogeneity comes into place, right? So in this case, you might have like these two issues. Like, first of all, like all features are not available at a particular node. And the second issue that could happen is that there are two different nodes, but features of node 1 are actually not applicable to another node, right? So you might have to do things like, okay, you will create a very long vector, I mean, of of features, and you will make something that is not applicable. You might mask it, but essentially you are actually complicating the solution itself. But the major central idea is some features are actually not even applicable for certain node setup. Okay, any doubt in this? Okay. Yeah, and as we see that, I mean, we have graphs, but graphs that we see in today's life, they are, a lot of these graphs are actually not static actually, right? So think of like a dating company. I'll take example of dating company, it's just easier. So a person has actually put two features. I mean, initially the company actually asked only for the age and the sex of the particular person. So this person actually entered 22 and female. As time passed by, the person decided, okay, I'm not going to show my age actually, right? So the person deleted the information of the age, so that feature is actually not available for them. For example, you cannot predict using that feature, you cannot train using that feature. Then over time what happened is, I mean, like COVID came, so maybe the dating company decides, okay, we'll add an option like are you vaccinated, so the person can actually do some filtering, etc., right? So the company decided, okay, let's add a feature called vaccination. So the person will be asked to say, okay, I'm vaccinated or I'm not vaccinated. Some people may not even update their actually status, right? So you have missing features, you have not available features, you might have features which are not applicable to you. And in the real scenario, it's actually a lifelong setup where actually features are going to get added or deleted over time. And even the values of the features can actually change over time. So you need a model which can actually learn over time as these things are happening, right? So you will have new nodes where new features can come up. All the features can be removed. Some features can be removed. Even some nodes can be deleted. So it's all a dynamic scenario where your graph can also change, and also the features in the graphs, nodes in the graph can also change. Okay. Any query in this?
So just a quick question, right? So when you have scenarios where let's say you have some attribute and then let's say the attribute is like some sort of product, right? You have like, does the user own like iPhone, and then each year you have new iPhone category coming out. Like, how do you deal with kind of basically you are kind of expanding your classes or like your node features?
That can happen. I mean, let's say a user, I mean, so in this case, are you assuming that a user is actually attributed by the phone he or she owns? Are you assuming that kind of scenario in this question?
Yes. So I'm thinking that like you could have attributes that basically it was like good for a chunk of time, and then you would kind of expand into new distributions. Let's say consider the new iPhone model as a new class or something, right? So you can start off as the range of like 0 and 10, and then you go to like 10 and 20 and so on. Um,
Yeah, it depends. I agree with your point. So it depends upon like I mean, business use case actually. So some
mhm.
company, I mean, the company might have actually like I mean, instead of discretizing to 0 to 10, they might have, okay, iPhone 1 or iPhone 2 or iPhone 3. So let's say timestamp 1, you had iPhone 1, right? Then you kept it that, I mean, you kept the same for, let's say, 7 years, right? And at the eighth year, you can say, okay, disabled iPhone 1. I mean, iPhone 1, actually, you just make the feature as 0, right? And in the eighth year, you will make iPhone, let's say, 10 as 1, right? So your features, I mean, your feature set can also expand in this case. It's a use case thing, but your feature set can actually expand. That can happen. Yeah.
Right, right. Thanks.
Thank you. Yeah, so there has been some work that deals with missing features and like lifelong learning for graphs. So there were some works which were like more of in a transductive settings where it was not possible. I mean, when we tried to adapt it, but it was not possible to adapt to new nodes and new features, so more of a transductive setup. And there has been some work on continual learning for graphs. But whatever, I mean, at this point, when this work we had started, at that point of time, to the best of our knowledge, it not have the capability to learn when you are actually adding new features or changing new features. Most were designed where your graph structure is actually changing and not necessarily the feature set or the features are changing, right? And there has been some work like which were doing like for tackling the missing value imputation. So as I mentioned, right? So if you take this scenario, like you have an item like soft drink, right? And let's say I have a feature of calories, milliliters. And if let's also have a feature like CPU cycle, technically you don't need to impute CPU cycle into the soft drink actually, right? It's not a relevant feature at all. So it's technically not applicable. So if you try to impute it, then actually you're almost trying to add something which is anything away from not applicable is actually noise in this context actually, right? So that was our main concern. And if you use this means that actually you're actually imputing irrelevant features that when we tried initially, it was leading to more like noisy predictions because they were actually not applicable to those kind of particular nodes in the graph. So in this work called as graphene, so graphene comes from like allotropic form of carbon, graphene and all. That's the reason behind this name. So think of like you have three nodes in the graph, v1, v2, v3, and let's say you have three features for simplicity, f1, f2, f3. And if the value of a particular feature is available, let's say we make it green, and if the value of a certain feature or that feature, for example, is not available, you just keep it red. Okay. And what we did was, let's say we removed the unknown feature. So let's say f3 was not available for v1. Let's say okay, we don't have f3 for this particular node v1. And similarly for v2 we removed f1, and similarly for v3 we removed f1, f2. So we are not doing any sort of imputation here. Let me just be clear, we're not doing any imputation here. Okay. Now we'll come to how it works. So our goal is we want to decouple the features from the GNN parameters. So if you think of existing GNNs, right? So your input hidden layer is almost like a kind of a function of the number of node features, etc. you have, right? So what we did was we treat each actually a node as a feature as a node actually. So if you remember, we had like removed f3 from v1. So let's say v1 has two features, f1 and f2, and you have two values, 0.2 and 29. v2 has two values like for f2 and f3, 37 and 1. Similarly, v3 has available feature f3 with value 1. Now what we do is like a transformation. So we make kind of almost like a bipartite graph where we have graph nodes on one side, like v1, v2, v3 on one side, and the feature nodes on the other side. So what's the feature nodes? So whatever features were available, we make a node out of it. So f1 becomes a node, f2 becomes a node, f3 becomes a node. So how do you assign value to, how do you assign feature to values, right? Features to values, right? So if you see v1 at feature 1 had value 0.2, right? So we make an edge between v1 and f1. So if you see v1 f1 has edge attribute 0.2. So in this case, the value of the feature is going to the edge. And how do you know this value is of this particular feature? Because there is an edge between v1 and f1. Okay. Now v1 does not have feature value 3, right? So you will see there is no edge between v1 and f3. Is this part clear? So wherever there is a feature available, you connect that graph node to the feature node. So any doubt in this transformation? Because very important. Any doubt in this?
Can the features also have interdependencies? Let's say you have a salary and occupation. You have like doctor as salary, and then yeah.
In the current work, we tried to get this working, but as of now, empirically did not help. But your intuition is correct that these features also can have dependencies. They can have. We tried empirically that experiment also. It did not help in improving the performance, but there will be data sets, I'm pretty sure, where this dependency should ideally be captured. I agree on it.
Thanks.
So this is how the transformation is. Wherever you have for a particular node, you have a feature available, you make an edge from that node to that particular feature node and add that value on that edge. Okay, that becomes edge item. Okay. Now, once you have the transformation, what actually this transformation offers, right? Like you can actually have a non-identical feature set for each node. So let's say v1 actually can have only two features, f1 and f2. So remember the example of soft drink, right? So let's say f3 was your CPU cycle. So f3 is not relevant for what shall I say, cola drink, right? So you only connect to those features which are actually relevant for you. Okay, so heterogeneity can be handled with this architecture, and you don't really need to impute. There is no need for imputation, and you can just directly end-to-end train in the case of missing feature scenario. That is how we did actually. We just get the embeddings, and then we perform whatever loss function that we want to. We'll come to how we get representation of this of the nodes in the graph. And another advantage that this architecture offers is that lifelong learning is possible. So as I mentioned, that these graphs are continuously changing over time, right? Like some person is removing edges, some person is actually like removing some feature, disabling some feature, some person is coming up with a new feature, the company is coming up with a new feature. So if you want to, let's say, add a new feature, right? So what you do is just add a new, let's say F4, right? And you connect it to V1. So whoever has actually put value for F4, you just connect to it and add value. Somebody doesn't want, I mean, somebody has not actually updated their, let's say, feature. For example, you had a feature 4. Somebody doesn't want to update that information. Okay, leave it. There is, don't put an edge actually. So you can actually, I mean, as your graph is changing, your features can also change in reality, right? So this architecture allows us to do that task. Okay. Yeah, so now how does the message passing works in this case, right? So if you remember, you have, let's say, 3 nodes that are called graph nodes, and these are like feature nodes, right? So how do you initialize? So what we did was, for the graph nodes, you make all of the embeddings as 0. You can put any number, but we put all initial embeddings as 0. And for the feature nodes, you need some embeddings, right? So we just put like a trainable layer, which can also be expanded as you actually add new features in the graph. But when you add new features, you need to do some training. I mean, you cannot just add a new feature, but if you add a new feature, you need some new training also to update the embedding layer also, right? And so what we do is, I'll just show you the how message passing works in this context. So first is step 1. So there are some graph nodes on the left side. There are some feature nodes on the right side, right? So in the step 1, we pass the message from the feature nodes to the graph nodes. Okay, one layer of message pass. You pass the information from the feature nodes to the graph level nodes, right? Now, the graph nodes have the information of the feature nodes, right? Now, what you do is, these nodes have information of the feature nodes. Now you do a simple message passing like you do in any GNN, right? You do message passing from the graph node to the graph node itself. If you can see the step 2, right? V1 is passing message to V2, V2 is passing to V3, and similarly. So like a normal GNN, you just pass message from yourself, the neighbors, and the neighbors pass their message to you. Okay, so this is the step 2. The third step, what happens is, to complete this entire message passing layer, one layer of message passing, you again update the embeddings of the feature nodes based upon the information available from the graph nodes. So essentially, in one layer of message passing, you are doing 3 steps. First, you pass message from the feature node to the graph node. Then you distribute information within the graph nodes. Then again back to complete the message passing from the graph nodes to the feature nodes. That completes one layer of message passing. This you can repeat as many times as you want, right? So there is, I mean, it's like one layer of graphene. You can just keep repeating it. The more you repeat, the more further information you will aggregate actually. Okay. Any query in this?
There's a question in the chat. I'll just relay here. So the audience mentioned that they would like to review your presentation. Can you share the slides with everyone if you have a link or something? I can also upload it on Google Drive and then share it on the reading group.
Yeah, that I can do later once the presentation is over. I can share that. Yeah, sure.
Okay, sounds good.
Sure. Thank you. Anyhow, this also is present on the ICML web page. Also is present. So yeah, it's already there.
Okay.
Sure. Cool. Yeah. So is this part clear? The 3 steps of message passing?
Just one question. I think this makes the model much more complicated. Do you have some kind of?
So the point is actually, if you see, it works. I mean, so idea is, if you have a very high missing rate, let's say you have very low availability of features, right? Then it's not very complicated. But yes, if you don't have, if you have all the information in the graph, then probably it's more complicated. So yeah, there is a trade-off.
Okay, thank you.
So yeah, so once this, so as I mentioned, it's also inductive to unseen features. You just add a node and you keep updating the representation of all the nodes in the graph. So yeah, so how do we evaluate is like first we as discussed in the previous slide. So we test its robustness against various missing rates, like very low missing rate to very high missing rates. We tried like what happens if you use different GNNs in this message passing framework, and how does the model perform when you train it in a lifelong fashion over time, okay, when the features are changing, etc. So if you see this table, then I mean for our presentation we are showing two data sets, Cora and Sites here. And p is equal to 0 means there is no feature missing. P is equal to 0.5, that means we randomly remove 50% of the features, and 99 means it's a very high missing rate. You almost remove all the available features, right? So NM is neighborhood mean. It's a baseline where for each node, if the feature is missing, you replace it by the average of the neighborhood. FP is feature propagation, which came in like I think last year LOG conference. So we observed that, I mean, when the feature missing rate is pretty high, for example, 0.99, then graphene performs pretty good. Similar is the scenario with like sites here also, that when the feature missing rate goes really high, then yeah, the performance of the proposed architecture actually is clearly evident. When then, especially when the feature missing rate is pretty high. And yeah, we also tried like what happens if you replace the GNNs that we have like GAT or GIN or GraphC, etc. In general, in most cases, when the feature missing rate was high or even like not very high too, even then graphene was actually outperforming the other baselines. And we also tested its performance in the lifelong fashion. In the lifelong fashion, we actually had to do one more thing. So there's something called elastic weight consolidation. So what happened? So what we did was, so when the graph was changing, or like the graph feature or the graph structure was changing, we preserved a small number of samples in the graph. And our objective was, if you are updating the parameters of the model when like the data changes, then we wanted to, I mean, there are some parameters that might not be very important for the unchanged graph, but there might be I mean, if you have not changed some part of the graph, then then the performance of the model on that part actually might suffer actually, right? Because you are updating the parameters of the model using the only the, I mean, the delta part of the graph, right? So our objective was, can we prevent significant updates on the parameters of the model that are important for the unchanged part of the graph, right? So we applied elastic weight consolidation, and we prevented significant updates on the model parameters that are very relevant for the portion of the graph which has not changed. Okay. And so we did not have any real data sets except one, that is DBLP. So what we did was, we synthetically removed some features, removed some value of the features, added some value of the features, etc., at different timestamps, and updated different models. So what we saw was our proposed model, for example, this GNN actually was able to maintain its performance on the entire graph, the test accuracy on the entire graph when the graph was changing, the features were changing. So on this red plot is actually called Oracle. Oracle means whenever there is a change in the graph, you retrain the entire graph, right? So we don't want to do that, but it is a way to benchmark the full performance actually, right? So what we observed was the green color, that is our model, continual graphene. It was able to reach a good performance at different timestamps when the graph was changing. Similar happened with DBLP. So DBLP, the point was the graph was actually growing. I mean, nodes were coming, edges were actually coming. So initially the performance for everyone was bad, but as the graph was changing, new nodes and new features and new edges were actually getting added, the performance of what shall I say, continual graphene, the green color, actually was improving over time. It was like almost like Oracle, but eventually, as you can see at the 6th timestamp, Oracle actually, I mean, retraining was actually giving the best performance in this case. But yeah, it was able to beat simple baselines like ER is the the experience replay baseline. FT is fine tuning that actually, I mean, if you update only, let's say 5 nodes, you update the parameters of the model using only 5 nodes. So this leads to a problem called catastrophic forgetting, which is very common in lifelong learning, that if you learn something new, you forget the past. So when you do only this fine tuning, that is FT, if you can see the blue line, the performance actually keeps going down, because actually you're updating the only a small portion of the graph, but your model is not aware of what happens to the other part of the graph, right? So your model starts learning new patterns, but it forgets the old patterns. So it's a very common problem in lifelong learning. Yeah, so the key takeaway was like we were able to develop a model which is like assumption free and gene agnostic. It can operate with different GNN also, and it can also support continual learning, where you can, I mean, your features can keep changing over time, nodes can keep changing over time. And it was inductive to both nodes and features. You can actually add or destroy nodes, add features, remove features, change the value of the features. And yeah, we also tried on empirically evaluating on real world data sets, and we saw, okay, yeah, in many cases it's able to outperform the existing state of the art methods. Yeah, so we also made our code public. You can try it out. We have made readme and all, so yeah, it should be you should be easily able to execute it. Yeah, so yeah, thank you for inviting me for this talk. It was a pleasure. Thank you very much.
Yeah, thanks for the presentation. I think there was also a question in the audience earlier about if the feature nodes can are going to be too dense, especially you have features for like everybody, then that might affect the message passing framework.
Yeah, so yeah, agree. It's a very, very interesting question. So so one second, let me just share the result table again. One second. I'll just take the other question also, 1 minute. So yeah, so what happens is when if you can see this slide, I guess this one. Yes. So when the feature missing rate is, I mean, there is no missing rate actually, right? So P is equal to 0. Yeah, we do see that sometimes you don't need our architecture. If you see the Cora on Graphene, the plain GAT actually outperforms us. So when there is, I mean, there is no feature missing at all, right? So we do see cases where a plain GAT architecture can outperform us actually. Yeah. So yeah, so I would recommend it to use more when there is a missing rate actually. Yeah, so then it's more beneficial in that case. Yeah. So other question I see, can you share more details about Oracle GSH? Yeah, so 1 second. So Oracle GSH is actually you retrain everything. It doesn't have the graphene architecture, it just have a normal GraphSeed architecture, but you retrain the complete what shall I say, the complete graph, even if you change only slightly. So as I mentioned, there is a problem in continual learning called forgetting. So the performance of a lot of methods goes down because you are updating only a very small portion of the graph, right? So if you update, let's say you have 20,000 nodes in the graph and you just update 5 nodes, you perform gradient descent, your model might do very well on these 5, right? Or neighborhood of these 5 nodes, but it might forget what it learned on a portion of the graph which was very far from here, let's say, which was not related to it actually, right? So, but when I say Oracle means even if 2 nodes are changing in the graph, I'm going to retrain the entire graph. So it's almost like you train from scratch. So it doesn't suffer from catastrophic forgetting, and it is technically the benchmark you want to achieve. It's not that easy, but it's the benchmark you want to achieve. Yeah.
I hope, Sahil, you're not referring to Oracle as an Oracle corporation.
No. Oracle means
okay.
Oracle means like you can think of like almost like ground truth where you retrain on them. That's like the benchmark. Yeah. Okay. It's okay. It's a very common practice to use Oracle in this context actually. So yeah. Okay. Yeah. Okay. Sure.
Because Oracle do have a graph database, right? Within the Oracle database. Right. So I was just surprised whether you're using Oracle graph database for your research perspective.
Oh, thank you very much for introducing me to it. I'll take care of it next time. I'll mention Oracle here. Thank you very much.
Yeah,
It was a very, very interesting question.
yeah. By
Sure.
the way,
I'm a
I'm
bit
from
clear
Oracle.
now. Yeah.
I'm from Oracle, so that's why I'm a bit surprised.
Sure.
Anyway,
Sure.
good.
Sure. Thank you very much for the question. Thank you. Yeah. So in general, I mean, the idea is, I mean, in continual learning is you want to learn only with the updated data as much as possible. But generally, people are still struggling to achieve that Oracle level performance. It's still not, people are still not close to achieving that yet.
Yeah, it's basically the upper bound for continual
Yeah.
learning. And
Yeah.
most of the methods here, like experience replay and even the EWC, which has been a quite old method from continual learning. So there still seems to be a struggle on like how to get the good performance for continual learning setup.
Actually, there is a paper, if you could just Google, called GDUMB, GDUMB. I'll just write it, GDUMB. So it's, I think, last 1.5-year-old paper. It's on archive, and it just did a like almost like random, randomly sampled like experience replay, right? And it showed like it outperforms a lot of these complicated methods. So it was like random is really very good. Actually, it's like random is very. It's like a dumb paper which outperforms everyone. So that's how, I mean, their main objective was. Yeah.
Mhm.
So there's a question, do you have your scripts anywhere on GitHub? Yeah, so the code is, I mean, if you want, you can scan this. Yeah, so this is the code, the QR code. If you scan this, it will take you to the repository.
Yeah. And I think it's very interesting paper, and the idea are quite intuitive. So thanks so much for presenting it. How do you think this can be extended to temporal graphs where like currently the assumption is that the graph structure also changes, but it's more like discrete, right? If you have like a continuous time dynamic graph or just an edge stream with features potentially on the edges, then the setup might be a little bit more difficult. But yeah.
Could be. So in your case, I think that's a very good question, I would say. So let's just open it so it's easy to understand. So in your case, what you're saying is that there are also edge features, right? So in that case, what you can do is, I mean, first part, I'll just take the second part first for edge features. So in this case, we did not have edge features, but you can actually have edge feature on the graph node. So when you have V1 and V2, you can have the edge feature here also, actually. So this not a big task, because for example, the GNS that we use did not require edge handling the edge features, but if you if you just simple like PyTorch geometric, right? So in PyTorch geometric, you have the GAT layer. The GAT layer can also handle edge features, right? So if you just use that particular GAT for the message passing within the graph nodes, right? So as I mentioned, there are three GNNs, right? There are three GNNs operating, right? So for this part, use a GNN which actually can handle edge features. So you can actually just, we don't know how will it perform, but I think it should be doable to handle edge features in this case. And the other question that you had was like your graph changes temporally, and edge features are also there on the, I mean, the time features are also there on the, I mean, the edge timestamp, right? You're talking the edge time, I mean, when the interaction happened, right? That part, right? Like V1 interacts with V2 at a particular timestamp. So I'm not that good in it, but I'm not sure if like papers, like I'm not sure, you know, TGAT, there's something called temporal GAT and all. Sorry?
Yes. Yes.
I'm not sure if it can be easily applied on this task with replacement of this, but edge features, I'm pretty sure can be handled by replacement of a GNN which can handle edge features. That should be doable, easily doable.
There's another question that I was thinking is, wouldn't like depending on like how many features you have, and wouldn't it potentially cause more problem for over smoothing in GNNs? Or like there's also issues where GNNs you have a fixed, like the nodes have a fixed encoding, like a fixed size hidden dimension, right? So now you are pulling over all the feature dimensions, which is fine, I guess, but it was kept separate from the node embedding before. Like it was having just a node feature, and now it's pulling full message pulling. So you're pulling these, and then you are sending it back, right? So it's kind of adding another neighborhood on top of what the GNS need to deal with. So you have so let's say you have a central hub node,
right?
where you have a lot of connections in the graph already, but now you also have the features you are pulling over on top of that.
Yeah, so essentially in that case, so what we are doing right now is we do concatenation. So if I'm getting a message from two components, right, I don't add up, I just actually concatenate. So now it's for the neural model to figure out what to do with the concatenation. So I have my own embedding and I have embedding coming from the neighborhood, right? So I have my embedding from the previous layer and my information coming from the neighbors in the current layer, right? So I concatenate them actually. So initially, as you mentioned, I mean, if you are putting, I understand your question that you are putting too much information in one dimension thing, right? I mean, one like 128 cross vector, right? But that, I mean, in that case, okay, if you would have added that information, like adding, like doing a summation over the two embeddings, it might have not worked well. In this case, we just actually concatenate the information actually. So maybe that was the reason it worked. Adding might have, I mean, or other concepts. I mean, if you're trying to put everything in just one vector, maybe it would have not worked. I agree. That's why initially we tried concatenation, and that operator maybe yielded better results. Maybe that is one. That is one reason. Yeah.
Okay, thanks. There's also a question from the audience. I think Pharma, do you want to ask the question yourself?
Yeah, I was actually checking the paper. I was wondering whether you have any kind of analysis on the training time or complexity of the methods.
Training time, empirical, we don't have. We do have computational complexity of the graphene architecture that is already there, but we don't have like we can actually run it. We didn't actually put it in the paper, I guess. We didn't put it in the paper, I guess. I mean, we didn't actually even what shall I say, compile it ourselves also for now.
And I mean, just when you run
it will be slightly higher. It will be slightly higher. Slightly higher. I mean, if you just run a simple graph stage, right?
Yeah.
Versus green on graph stage, it will be slightly higher. It is from whatever experiments that we ran, it will be higher. It will be slightly higher.
Thank you.
Especially when your feature missing rate is not high, then I think the experience it was slightly high.
Okay. If there are any more questions from the audience, so feel free to ask now. We still have a few minutes. Okay. So if not, then maybe we can wrap up the talk for today. It's very nice to have you here, Sahil, and then like excited to see your future work as well. And thanks for joining, everyone. And then I'll see you next week at the reading group.
Thanks, Andy. Thanks, everyone.
Thank you.
Bye-bye.
See you.
Thank you. Bye.
Bye.